Now we're live. So now let me wish you good morning. Hopefully I'm not the first. It's 11:30. Morning's almost over. Hopefully you have people in your life who are wishing you well. So anyways, we're live. We have this is the third. Oh, there he is. There he is. Oh, no, let me get back over here. Good morning, Raj. We have three. There we go. There's the live stream. I'm just pulling it up on my second monitor. So, did I spell? Okay, yes. For a split second, I was like, did I spell morning right? But if I added the U, then we would be in morning this morning. And I'm not gonna lie, I'm in mourning just a little bit myself. After we finished class on Monday, I walked out of the office, and I was like, it just hit me all of a sudden. I told my wife, I'm like, this is the second to last week of this semester. I only have 3 more classes left, and I was like, this Gen Chem class has been awesome. Like you guys have been awesome, and I got really sad all of a sudden. I'm like, I am gonna miss this class of students. So stinking bad. So anyways, I hopefully see you around campus. Hopefully you stay in touch. Because you guys have been awesome. Let's see. Oh, not sure if I answered it last office hours. Oh, okay, yes. Ryan, I don't think I did. Let me hit that up. So let's see. Your question is about the structure of antimony SbH5, antimony pentahydride. Okay, yes. So how? Okay, I don't understand how there is any lone pairs of electrons. It seems 500. It does. Yes, it totally does. If you look at the so if we do old school Lewis structure drawing, right? We have antimony, which when we look at the periodic table, has 5 valence electrons. And then we have hydrogen, which we know brings 1 each, and there's 5 of those. So our total electron count here is 10. Antimony is going to be our central atom because it can make the most bonds. All right. And then next step is we need to attach all of our lone pairs, all of our atoms to our central atom. And this is going to take 2, 4, 6, 8, 10. So that's going to spend all the electrons in our budget, leaving us with 0. So this is the Lewis structure. And if we wanted to draw the VSEPR geometry, we've got 5 electron groups, which would make this molecule trigonal planar. So the 3-dimensional representation for this molecule would look like this. I said trigonal planar, holy moly. Trigonal bipyramidal, because we have 5 electron groups. So Ryan, you were absolutely right. Let's see. In the VSEPR lecture, I showed it with 5 H's and 1 lone pair. Let me see. 2. It's entirely possible that I did. If I did, then I made a mistake here. Let me try to pull up my lecture notes so I can see what I did. Because it's entirely possible that I messed that guy up. Let me check Ryan real quick. Let's see. Let's go to my COVID file. Interesting. Okay. It could have been I forgot a negative charge. Let me check what I did, because I don't remember exactly. Okay. This would have been. Sulfur. Let's see. Okay. Ryan, great catch. I did totally make a mistake. The problem is in the notes. Let's see. Let me open a new slide. In my notes, it should have been SbH5 -2. So I forgot to write the charge. So you're 100% right. Oh no, dude, thank you so much. Yeah. Thank you so much for bringing it up. With that charge in there, then the Lewis structure will be exactly the same, except that we will have a lone pair on our antimony, right, and a charge. And now we have 6 electron groups. One is a lone pair, and that's why we end up with the octahedral electronic geometry and the square pyramidal molecular geometry. Totally. No. Thank you so much for drawing attention to this, because I guarantee that you are not the only one who will see that and get confused. I'm just writing myself a note real quick. I'm gonna go back and correct the lecture notes, so that the lecture notes on Canvas, for anyone looking at it, will read the same. And I'm also going to post a note in the video next to the timestamp, just letting everybody know what the mistake is. So when you go back and watch it, or when people go back and watch it, hopefully they'll see that and not be confused. But awesome, thank you so much for bringing that to my attention, because those corrections are helpful. Totally. I'm so glad. You totally rock. Okay. All right, cool. Well, hey, that is a good way to kind of kick off our day. Do a little bit of Vesper review. I will be posting those updates a little later this afternoon. Oh, awesome. Yes. You see, that is the beauty of asking questions is when you ask a question, you're actually asking for a cluster of people. It's always whenever you ask a question in a class, more than one person has the same question. So it's a way of being a generous classmate by being the one willing to ask. Let's say, okay, Raj, you got a quick question. Am I going to curve the grades at the end of the year? Raj, great question. I have no idea, honestly. I honestly will have no way of knowing until I get there. It's it's something that I will definitely consider, but I need to kind of get all the graded assignments in, look at how everyone was doing in the lab. Here we have two different lab instructors, so you know, making sure that their grading is kind of on par with each other, and there's a lot of different factors that I consider, and obviously the global pandemic and the emergency switch to you know, turning me from a professor into a YouTuber, all of those things will be taken into consideration. No worries. I'm pretty sure you're the only one that missed that actually like is like, oh man, I missed the 420 office hour. Because I don't think my 420 kids are coming to that anymore. But anyways, it's something I'll consider at the end of the semester, but there's a lot of different factors that I look at. So I can't commit right now to saying yes I will or no I won't, just because my information is incomplete, my data is incomplete. All right. So okay, so what I had a thing. I know I had a thing. Oh, I have news. So I finished I finished your multiple choice exam. Your multiple choice exam 3 is complete. So after lecture, I can give, we can talk about that. I can give more details. I haven't picked the time yet, how long I'm going to give for the exam, but I have all the questions written and all the problem banks, so that helped me feel accomplished. Another item of business. Our mixtape today is a different one. I'm not sure how many of you are familiar with the artist Nick Cave. But he's definitely unique. Definitely unique. He's been putting out music since before I was born. Actually, his album came out 2 years before I did, and first album. And even though he's put out music in the 80s, 90s, and 2000s, 2010s, I don't know what they call that decade, the one we just finished, his music doesn't sound like it came out of any of those. Yeah. It's so strange. It's like there's nothing to really compare it to. So I made a playlist. If you haven't ever heard of him, check it out. If you have heard of him, you can be like, oh, these are Josh's, a couple of Josh's favorite Nick Cave songs. A couple of them are from a band named Grinderman, which he did as like a side project, but I liked a lot. Anyways, very different. And I can't try to describe it, so I won't. All right. Okay. Now the one last thing that I want to say is, so today we're going to start intermolecular forces. All right, and we'll be finishing this on Monday of next week, our last Monday together. But before we do, I wanted to take one last wave one last goodbye to hybridization. All right. All right, and normally what I do at this point in time is I tell the class, okay, here are the two ways that you will be tested on hybridization on the exam, and this semester, what I will say is here are two of the ways, but I'm not guaranteed. There may be another thing that I come up with. I'm not sure. Mostly because so I've written the multiple choice exam, but now I've got to write the different versions of the take home exam, and I'm not exactly sure. I know that these two forms of problem will show up on the take home exam, but the challenge with the take home exam is you have to kind of elevate the problems. You got to make them next level a little bit, and I'm not exactly sure how I'm going to do that with hybridization. So these two problem types will be present, but they may not be the only types. There may be another way I can cook up to test on hybridization. So this is not an exclusive list, but these problem types are guaranteed to show up. The first is you'll run into a problem that says draw the three-dimensional representation of the bonding orbitals and those are these are our beloved balloon animal problems. All right, these are the ones that we were doing for all of last lecture. All right, I will totally ask you to draw the bonding systems of, sp3. You'll see this for atoms that have sp3 hybridization, sp2 hybridization, and sp hybridization. So you'll see all of those. You may see all of those. All of those are fair game. I can ask you to draw the bonding systems for those atoms that have these hybridizations. All right. The second way that you'll definitely be tested on hybridization is you'll be asked to label the hybridization of every non-hydrogen atom in the following molecule. All right, that is another way you'll be tested on hybridization. And I finished, as I've already mentioned, the multiple choice exam. And there are definitely problems on the multiple choice exam where I ask you to determine the hybridization of a central atom in the molecule. But I just realized I spelled label. But that's not the only. I'm not only going to give you on the take home exam molecules with with just a central atom. So I'm not going to do this here and now, but I will draw it. And you can try this on your own. So you can try labeling the hybridization for each non-hydrogen atom in the following molecule. You're like, where is this going? Only fun places. Yeah. You know what? Don't be scared. How bad do peeps typically do on these problems? Oh, here, Raj, I'll get to that in 1 second. So I'll ask you to do two things. One, label the hybridization. And then the second thing I'll actually ask is determine the number of sigma and pi bonds in the molecule. And again, I'm not going to do this one here. I'm putting this here so that you can try it on your own. Maybe we can talk about it in office hours. You can take a crack at it, and then if you want to see it kind of explained a little more, we could do that there. But the reason why I wanted to put this here is this problem is a 100% exam caliber. When I write it in green, it makes it feel like, oh, 100% grass-fed organic beef. Actually, Raj, this isn't a butane. It's a 1, 2, 3, 4, 5, 6. It's a 6 carbon chain, which would be hex. But it's not a tane because it's got a ketone, it's got an alkene, then a couple weird substituents, an alcohol, and whatnot. So, anyways, Raj, to answer, or Diana, to answer your question, how well do peeps typically do on these problems? It totally depends on the clarity of their drawing for the balloon animals. For problems like this, people typically do pretty good. Anyways, I wanted to throw this at you. This is an exam caliber problem. You will see something like this. I don't know why I said might. You will see something similar to this problem on the written exam. So anyways, again, I'm gonna let you do this because working this on your own will be an exam simulation, right? It'll be you, without me, trying to solve this problem. And then if you want to see it explained, we can go over it in office hours. We can talk about it. But I think that you will get more out of it if you try it on your own first, and then get a little explanation. So, anyways, label the hybridization of every non-hydrogen atom and determine the number of sigma and pi bonds in this molecule. Exam caliber, you saw it here first. All right. So now we're with that last sweet goodbye to hybridization. Again, we're not done with it. It'll be on exam 3 in the final, but we're done formally talking about it in class. We're ready to start the last topic of the semester, and that is the topic of intermolecular forces. Intermolecular forces. All right. Now, this is intermolecular forces these are the attractive, it's the what they are is they're the attraction that molecules feel the attraction molecules feel for other molecules. All right, they're the attractive forces that pull molecules together. All right. This intermolecular forces determine physical properties. All right, the intermolecular forces that a molecule experiences will determine things like boiling point, melting point, surface tension, solubility. All these things are controlled by the intermolecular forces that a molecule feels. All right, and we are going to look at 3 different types of intermolecular forces. All right, the first is called London dispersion forces. All right. London dispersion forces. Sometimes you may have heard these called just dispersion forces or van der Waals. He's a Dutch guy with 2 A's in his name. Van der Waals forces. Another name this goes by, depending upon who taught this to you. So, Raj, we are going to crack into Chapter 12 a little bit with kind of polarity, but we're definitely not covering the entire thing. And also to answer your question, or a comment on your question, the ACS final exam only covers chapters 1 through 11. So we've completed chapter 11. We're cracking into chapter 12 a little bit, but as far as we're going to get our intermolecular forces, because that's just the time we had. All right, so the first is called London dispersion forces. The second intermolecular force we're going to learn is called Dipole-Dipole. Forces, and then the third intermolecular force we'll learn about is something called hydrogen bonding. All right, and just like we did with hybridization, where I gave you the punchline first, and then we came back and looked at the why. I'm gonna give you kind of the big picture out the gate. With these three intermolecular forces, they're already arranged from weakest to strongest. All right, so we have London dispersion is the weakest force, hydrogen bonding is the strongest one, and dipole-dipole is in the middle. All right? Okay, so again, intermolecular forces are the attraction that molecules feel for each other. It's what pulls molecules together. And we will take these one at a time, starting with London dispersion forces. Which I abbreviate as LD, London dispersion. All right. So let's talk about London dispersion. All right. Now, London dispersion forces. So I want you to, for a minute, envision a helium atom. All right. Let's think about a helium atom. Now we've got, in a helium atom, we've got 2 protons and 2 neutrons in the nucleus, and then in its 1s orbital, we've got 2 electrons buzzing around, right? Two electrons hanging out in that 1s orbital. All right. Now, when you think about the electrons, they're both attracted to the nucleus, but they're both repelled by each other, right? They're both repelled by each other. They're going to spend most of their time, they're buzzing around the nucleus. They're going to spend most of their time as far away from each other as they can get, right? They have to share an orbital. That doesn't mean they have to be all up in each other's grill. They spend most of their time as far away from each other as they can. But remember that the electrons never stop moving. They're just buzzing around. They're like Sonic the Hedgehog. They create this blur as they move. So it's not like they're sitting still. That means at different moments in time, there's going to be instances where as these electrons are kind of like buzzing around, that the electrons will find themselves on the same side, in the same region of the 1s orbital, right? This electron's going to swoop over here, and the electron-electron repulsion is going to force that other electron to move over to the other side, right? Because they repel each other. But what I want you to do is imagine we're watching a video, and let's freeze frame here for a split second. All right, for a split second, let's pause our video and look at the helium atom at this moment in time. After the one electron moves over, but before the other electron is repelled to the other side of the orbital. At this moment in time, what we have in the atom is an imbalance of charge. You can see that there's a negative charge built up on the left side of the molecule, and then there's no negative charge. There's an absence of negative charge on the right side. In fact, there's the nucleus, which is positively charged. All right? You don't have an even distribution of negatives and positives. You have the negatives concentrated on one side and the positives concentrated on the other. For this instant, for this moment in time, that separation of charge, that imbalance of charge, creates a partial negative and partial positive charge inside the molecule. We say that on the left side of the molecule, there's a partial negative charge. And then on the right side of the molecule, that there is a partial positive charge. All right. This weird squiggly symbol is a lowercase delta. It's the Greek letter that makes the D sound. It's a lowercase delta, and it's used to indicate partial charge. Not a full-blown charge, but a partial charge. All right. Now, for this instant, there is a partial negative on the left side of our helium atom and a partial positive on the right side of the helium atom. All right. Now, I want you to think in this moment, for this moment of time, I want you to think about the effect that this partial negative and positive is going to have on a second helium atom, on the helium atom right next door. All right, another helium atom, same number of protons and neutrons in the nucleus, all right? But let's think about where the electrons in this helium atom are going to go. The helium atom on our left, right, the very first one we drew, has a partial positive charge on the right side. Is that, now ask yourself, will that attract or repel the electrons for our new helium atom? And the answer is, as you know, it's going to attract them. These electrons are going to be drawn, pulled towards that partial positive charge. All right? They're going to get yanked to get close to that partial positive. And guess what that will create in our new helium atom? It'll make a new partial negative on the left and a partial positive on the right. What effect will this have on the helium atom 1 over? And you can already see where this is going. This is building. This is going to daisy chain as the separation of charge in the first atom will create an uneven charge distribution in its neighbor, which influences its neighbor, and so on and so forth. All right? So we can see in this new atom we'll have a delta minus over here, delta positive on the other side. All right. Now this, what about the atom below? So the atom below, so okay, great question, Vraj. It influences the atoms around it. Now the atom below will probably have its electrons drawn up towards the nucleus, so its electrons will kind of like bend up, and so it'll have a negative charge on the top and a positive charge on the bottom. That'll influence it, the electrons around it. This is all like one giant three-dimensional daisy chain. All right. Now, the attraction between the partial negative in one atom and the partial positive in the other, this is London dispersion forces right here. All right, that is what we're talking about when we're talking about London dispersion forces. It is the attraction between partial positives and negatives. All right. It is the attraction between temporary partial charge. That is what we're talking about when we're talking about London dispersion forces. The attraction between temporary partial charges. Now, here's the thing. So that is that temporary partial positive negative charge pulls these madams madams and sirs, pulls these atoms together. All right. Now, here's the problem. These partial positive and negative charges only exist for an instant. Remember, these electrons are constantly moving. They're constantly budging. We just paused that video to analyze what happens when they're both on the same side. But guess what? These electrons aren't going to stay there. Once we click unpause and let this go again, those electrons are going to snap away from each other, destroying the partial negative and positive in the first one, which will repel the electrons in the next atom over, destroying its partial positive and negative, which affects the one next to it. That's why London dispersion forces are weak. All right? They're weak because the partial positive and negative charges are temporary. All right? Yes, Diana, that is correct. That is 100% direct. Direct and correct. So here's the take home for London dispersion. All right? London dispersion. Kind of our take home bullets. First, the partial charges are temporary. That is why London dispersion attraction is weak. All right. And then the second bullet to take away from London dispersion forces is this. Everything with electrons experiences London dispersion. All right. So if I ask you, if you're doing, for example, the multiple choice on Canvas, and you come up against I give you a molecule, and I ask you, determine the intermolecular forces in this molecule. The answer must, if that thing has electrons, the answer must include London dispersion in the answer. All right. You can rule out in multiple choice, if it has electrons, it's got to feel London dispersion. So any answer that doesn't have LD is automatically incorrect. All right. Everything with electrons experiences London dispersion. It's weak, but everything has them. All right. Now, the last thing to keep in mind is this is the third and final thing. London dispersion is stronger. The attraction from London dispersion is stronger when the orbitals are larger. All right. They're stronger when the orbitals are larger. When the orbitals are big and the electrons have lots of room to move around, it's easier to create an uneven distribution because they can both be on the same side of the orbital and still not be forced super close together. So the larger your orbitals are, the stronger your London dispersion forces will be. So, for example, oops. So, for example, if I ask you to rank... Yes, Sulai, exactly. Dude, but you had that thought even before I said it. That is exactly it. It's because the electrons have more room to move, so they can both be pulled to the same side of the orbital, but if it's a giant orbital, they're not forced as close together if they're in like a 5s orbital as opposed to a 2s orbital, which is significantly smaller. So, if, for example, I asked you to rank the strength from strongest to weakest, for the following molecules. And by the way, the only molecules I'm giving you right now are molecules that that only have London dispersion forces, because we haven't talked about the other kind. So, if I asked you to rank the following molecules from strongest to weakest, and I give you N2, and I give you I2, and I give you S2, and Br2. All right, I want you to rank these from strongest one to the weakest one. You look at where these things land on the periodic table. All right, so let's actually resurrect our periodic table from the dead. Maybe pull it down. And let's find these dudes. So we're dealing with N2, which is right here. I2, which is made of iodine. Br2 is made of bromine. S2 is made of sulfur. All right. And when it comes to London dispersion forces, what we need to do to figure out the strongest ones will have the largest orbitals. So let's look at which periods they fall on. So this is nitrogen's on the second period, sulfur's on the third, bromine's on the fourth, iodine's on the fifth, which means that if we're going strong to weak, iodine has the largest orbital, so it will experience the strongest London dispersion. Next would be bromine, because it's on the fourth period, followed by sulfur, followed by nitrogen. So we would rank these strongest 1, 2, 3, and 4. All right. Okay, Diana. Yes, Viraj, exactly. Exactly. Does London dispersion happen more often for in liquid and gas states? Okay, great question. London dispersion is weakest in the gas phase, stronger in the liquid phase, and strongest in the solid phase. And the reason for this, is molecules, atoms, particles are farthest apart in the gas phase, so it's hard for them to get close to actually experience London dispersion attraction. They're closer in the liquid phase, so there's more opportunity for that attraction to happen. And then in the solid phase, they're all packed tight, very close, and so the London dispersion attraction is the strongest there. Totally. Okay, how are we doing? Not too bad. So this is London dispersion forces. All right. So that is London dispersion. Now let's take a look at dipole-dipole. Dipole-dipole forces. All right, now here's the deal. So with dipole-dipole forces, what makes London dispersion weak is the same thing, basically, that makes dipole-dipole forces more powerful or stronger. London dispersion forces are based on a temporary partial charge, the attraction between temporary partial charges. Dipole-dipole forces are and this is this, I abbreviate this with you'll see me using D&D to abbreviate dipole-dipole forces. They're based on they're the attraction between permanent partial charges. All right. So with London dispersion, there's this temporary partial charge that takes place in the molecule because the electrons just happen to be on one side of the orbital, but then it's gone. With dipole-dipole forces, there's something about the molecule that creates a permanent partial charge on one side and the other, and the attraction between these permanent partial charges is what we call dipole-dipole forces. Now, the question is what causes this to arise? How can we identify it in a molecule? And the answer to that is hooked into electronegativity. All right. So you'll remember. So there's a little bit of a review. We talked about this at one point when we were introducing bonding. We said that there are 3 types of bonds. We said that there are covalent, polar covalent, polar covalent, and ionic. And we said what determined which type of bond. Yes, Raj, that is correct. Did I misspell? Oh, man. Permanent. There we go. Thank you for the permanent. Ooh, double error here. Permanent. There we go. You could tell I wasn't an English major, right? Oops. All right, now I need emojis. Okay. So there are three different types of bonds, right? There's covalent, polar covalent, and ionic. And what determines what type of bond we're dealing with is the difference in electronegativity between the two atoms that form the bond. So the difference in if the difference in electronegativity is less than 0.5, the bond is covalent. If the difference in electronegativity is less than or equal to 2 or greater than or equal to 0.5, then we say that that bond is polar covalent. And when the difference in electronegativity is greater than 2, we say it's ionic. All right? Now, we know that in covalent bonds, electrons are shared. All right? Electrons are shared. We know that in ionic bonds, when we're talking about ionic bonds, we know that electrons are taken. What happens in this weird tweener, polar covalent, all right, you might expect, because it falls between sharing electrons and taking electrons, that it has some characteristics of both. And if you're thinking that, your intuition is spot on. With polar covalent bonds, electrons are shared unevenly. Electrons are shared unevenly. All right? So they are shared, but it's not equitable. All right? For example, let's say it was Christmas 1994 and your parents got you all a brand new Nintendo 64 with Mario Kart, and it's awesome, right? It's 3D games. It's blowing your mind. You can't believe it. The sad part is, because they're parents, they didn't know that it only comes with one controller. So you can't, without a second controller, obviously, two people can't play. And you are older. Maybe you're even the oldest sibling, and you're playing Mario Kart. And your younger siblings are being annoying because they want to play Mario Kart too, but you only have one controller. So, it's like you'd have to stop, right? You'd have to stop playing if they want to play. And you're just not, because you're bigger and you're older and you're having the time of your life. But your younger siblings are whiny. They somehow think that this setup is unfair. They complain to your parents, and your parents say, share with your sibling. Share with your sibling. And so you begrudgingly let your sibling hand the controller to your sibling. And you're like, okay, we're going to share now. But you let them play one round of Mario Kart, do one race for every 3 that you're doing. All right? That would be sharing unevenly. All right? That would be the type of sharing that goes on when we're talking about polar bonds. the electrons are being shared. It's not that they're not being shared, but they're spending more time around one nucleus than the other, right? And so they and so they as a result, when the electrons are spending more time around one nucleus, that nucleus develops a partial negative. That's a horrible Irish accent. And then the one that's getting less time with the electrons develops a partial positive. So partial negative around the one that has the electrons spend more time with, partial positive around the other. And that imbalance is permanent because it's based on the difference in electronegativity, and that permanent partial charge, those permanent partial charges create the dipole for dipole-dipole forces, all right? So this is the magic number that you need to remember. If your difference in electronegativity is between from 0.5 to 2.0, we're dealing with drama for somebody. If it's between 0.5 and 2.0, you're going to have a polar bond, which will have electrons that are unevenly shared. All right. So let's put this to practice. Let's take a look at this. Consider the molecule hydrofluoric acid. Oops. New slide. There we go. All right. When you draw this molecule out, it ends up looking like this. All right. And if we want to assess what intermolecular oh man, it's so not. When we want to determine what intermolecular forces are present in a molecule, first, we know there's always London dispersion, right? Because we have electrons in the mix. But to determine whether or not we have dipole-dipole forces, we need to look at the difference in electronegativity between fluorine and hydrogen. Now, fluorine has an electronegativity of 4.0, and hydrogen has an electronegativity of 2.1. So the difference here is 4.0 minus 2.1 comes out to 1.9. That tells us that our bond, the bond between hydrogen and fluorine, is polar covalent. All right, polar covalent. That means, so here's what that means. That means the electrons will spend more time around the electronegative element in this that participates in this bond than the less electronegative element. The more electronegative element is hogging the controller. All right, it's getting more reps on Mario Kart, so it will pick up a partial negative charge. And the less electronegative element will pick up a partial positive charge. Because the electrons are spending more time around the more electronegative element. It's pulling on those electrons harder. And so this has created a permanent, this has created permanent partial charges within this molecule. All right. And so we will have dipole-dipole. Now there's two ways of depicting it. So you've seen I've already drawn in my partial charges. Okay, Raj, great question. So you look them up. You look up the electronegativity numbers. You don't have to memorize them. You just look them up. I actually really like this. I just posted a link in the comments to a periodic table that instead of showing atomic numbers, shows the electronegativity numbers. So that's an electronegativity periodic table I like to use. Doot. Oh, wait. I was selecting a pointing finger, but I almost clicked on not the first digit, but the second digit pointing, which is not the message I want to leave in the comments thread of my YouTube channel. Yeah, you don't have to memorize these. You just look them up. I like this periodic table because you can kind of find the elements. They're in places where you're familiar with them, and go from there. So we have a polar covalent bond, permanent partial charges in our molecule. This will create dipole-dipole forces. Now, this is one way showing the partial positive and partial negative charges is one way to depict the dipole. Another way to depict it is with a vector arrow. All right. So I'm going to draw this here in green. You do your arrow pointing with the arrowhead pointing towards the partial negative, and then a little hatch marked through the tail end at the positive side. And this is called the dipole moment. All right. It describes the uneven electron distribution as a vector, and it's just another way of showing that charge, uneven charge distribution. All right. Now, this has an effect. The fact that HF has a dipole moment, this has an effect on how these molecules interact with each other. For example, if we looked at another molecule of HF, it would line up with the first one like this, because it would want to pair the partial positive side of the molecule with the negative side of the molecule, right? This attraction is the dipole. This is the heart of dipole-dipole forces. All right. So here we have the attraction between the permanent partial charges. This is dipole-dipole at work. All right. One thing you'll never see is molecules of HF lining up like this, because you're never going to place your partial positive together with your other partial positive. This is bad. All right, it's going to want to be oriented the other way. Raj, great question. You soon will see. It's actually my next example. So HF is a simple molecule. It's a very straightforward example because we only have one bond in the molecule. All right. When there's more than one bond, things can get a little tricky. All right. So let's take a look at H2O. All right. Now, water if we want to determine whether or not our molecule is polar, the first thing we have to look at is the electronegativity difference. And oxygen has an electronegativity of 3.5. Hydrogen, as we've already seen, has an electronegativity of 2.1, so our difference here is 3.5 minus 2.1. This comes out to be 1.4. All right, and this is definitely a polar covalent bond. All right, this is a polar covalent bond. That means that we will have a partial negative sitting up on oxygen, and each hydrogen will receive a partial positive. All right, now the dipole moment for this molecule is a little more complex than the previous one because of the geometry we're dealing with. All right, there is a small dipole vector that runs along the line of one bond, and then another dipole vector that runs along the length of the other bond. All right. But the trick when you're dealing with vectored quantities, and those of you who have taken or are taking physics already know this. Sorry, I keep fidgeting with this bond. I want to make it better. I think that, okay, I'm just going to live with that. Is any vector can be broken down into an X and a Y component, right? And you can see that with this bond, that the X component of the first one lies along there, the Y component's here, right? The X component of the the second polar bond, X component lies there, Y lies there. You can see that the Y component is parallel, but the X component, these are opposite, right? These vectors have opposite signs, so they cancel each other. Here, I'm going to shift this over just a little bit. They have opposite signs, so they cancel. These two in here have the same sign. And when I say sign, I mean positive or negative, right? They're pointing in the same direction. So they add. All right. So actually, I need to adjust things just a little bit. So for the dipole moment for water, the X components cancel, the Y components add. So the dipole moment for water is actually run straight up and down. The positive end is next to the nitrogens. The negative end is next to the oxygen. All right. So if you were to just draw a water molecule pointing in any direction, right, with any orientation, and you were asked to, if you were asked to draw the dipole moment for a water molecule would run like this, because the oxygen is the negative end and the H's are the positive end of the molecule. Oh, wow. Cool. So still a polar molecule because we still have an overall dipole, but the overall dipole moment of the molecule will be the sum of all the little dipoles created by each polar bond. Actually, Vraj, great question. But actually, it's the other way around. The geometry of the molecule is what causes, or I should say what determines the direction of the dipole moment. So the dipole moment doesn't cause the geometry causes the dipole moment. All right, now, so up to this moment in time, every example that we've looked at, if we've had polar bonds, we've had a polar molecule, but that isn't always the case. Take, for example, carbon dioxide. Which looks like this. All right, now, looking at our electronegativity difference here, oxygen has an electronegativity of 3.5, as we saw in the previous example. Carbon has an electronegativity of 2.5. So here, our electronegativity difference is 3.5 minus 2.5. Whoa. Which comes out to 1.0. Definitely the smallest electronegativity difference we've seen, but this still falls in the polar covalent region. So this is a polar covalent bond. All right. Now, that means that we are going to have a partial positive on carbon and a partial negative on each oxygen. So if we were to draw in the smaller dipoles for each bond, one would have a dipole reaching from carbon to oxygen, positive on carbon, negative on oxygen. But the other, though it has the same thing, has it pointing in the opposite direction. All right? These two, because they're pointing in opposite directions, cancel out. They cancel each other. All right? What that means is that this molecule has no dipole moment. So we say that this molecule is nonpolar. All right, nonpolar, i.e., it does not experience any dipole-dipole forces. All right? Yep, opposites cancel. Opposites cancel. So carbon dioxide is a molecule with polar bonds. It has polar bonds, but it is a non-polar molecule. It is not polar. It does, yes. Everything with electrons has London dispersion forces. Totally. All right. So that is really where dipole-dipole attraction becomes tricky, is you have to ask yourself, okay, first, do I have polar bonds? And if you do, that's great. but it's still not enough. There are examples of molecules that have polar bonds but are non-polar molecules. So if you have polar bonds, it doesn't guarantee that you're going to have dipole-dipole attraction in your molecule. You have to look at the molecule itself to see, do these dipoles cancel each other out? All right. Now, I'm going to make a flow chart. All right. So this can be a little confusing. And, it can be a little worrisome. Students can be like, I thought polar bonds equals a polar molecule. But it turns out when you're determining whether or not your molecule experiences dipole-dipole forces, whether it's polar or not, there's a two-step verification process, right? Just like with your Gmail account. So you want to follow this flow chart. So if you want to determine whether you have dipole-dipole forces or what we call molecular polarity, all right. These are the steps you want to follow. All right. First, ask yourself, are there polar bonds? Does there polar bonds? That doesn't make sense. Oops. Goodness gracious. All right. Are there polar bonds? All right, that is the first question you ask. All right, so we're dealing with a flow chart. It's either no or yes. If you do not have any polar bonds, your molecule is automatically nonpolar. All right? If it does have polar bonds, it doesn't guarantee that you're polar. You have to answer one more question. And that question is the molecule perfectly what I'm going to call perfectly symmetric? Question. And if the answer to this question is no, then you're polar. If the answer to this question is yes, then you are nonpolar. All right. But to answer this question, you got to know what I mean by perfectly symmetric. All right. When I talk about perfect symmetry, all right, because understanding this determines your ability to answer the next question. When I talk about perfect symmetry, what I mean is this. So the molecule must have the same group on every position of position of its electronic geometry. All right. That is what I mean by perfect symmetry. So, for example, if you look at the previous two molecules that we did, H2O all right, has the electronic geometry. This electronic geometry is tetrahedral, right? Which means that we're dealing with 4 electron groups. And the question that you ask yourself is, are there 4 of the same thing? On oxygen. And the answer is no. There's 2 H's and 2 lone pairs. For oxygen to have 4 of the same thing, it would either need 4 H's or 4 lone pairs. But since we don't have 4 of the same thing, that means, because this answer is no, that means our molecule is polar. All right. Now, let's look at CO2. Does this rule out everything with lone pairs? Diana, great question. The answer to your question is almost yes. I'm going to say yes with, I can think of one with 2 exceptions. Yeah, with lone pairs on the central atom. And I'm sticking to my guns on this one. Yes, with 2 exceptions, which I'll get to. All right. So let's look, before we talk any exceptions, let's look at carbon dioxide. Carbon dioxide's geometry, electronic geometry, is linear. And that means that we're dealing with 2 electron groups. All right. So you ask yourself the same question. Are there 2 of the same thing? on carbon, and the answer is yes. Whoa, whoa. Doot, doot. And because the answer is yes, when you have that perfect symmetry, then your molecule is not non-molecule, is nonpolar. All right. So that is that. Let me see. Let me look at our time. Okay. I think this is where, which we'll get to. This is where I'm gonna put a pin in lecture. Monday we'll continue with our discussion of intermolecular forces. We've covered almost all of dipole-dipole. So we will finish up talking about dipole-dipole forces on Monday, and then hit up hydrogen bonding. As always, I'm totally down to hang out and chill with you guys if you have things that you want to discuss or talk about. I can also, I know. It's crazy. I can't believe we're here. It's blown my mind. I have a little bit of information on the multiple choice exam that I'm willing to drop. Oh, Diana, you've got a question. When is homework due? Let me look at the syllabus. I believe they're due sometime next week. I believe homework 11 is due on Wednesday. Which would make 9 and 10 I think due on Monday, but let me check our syllabus here. Let's see. Nope, not fall 2020. Spring. 5/11. Let's see. Yes. So, and again, this is in the syllabus, but homeworks 9 and 10 are due on Monday, and then homework 11 is due on same dates of the syllabus. Due 5/13. Yep. Same as syllabus. Oh, right. Okay, so here's the breakdown. And I'm gonna be making a Canvas post eventually for the whole kind of exam, rather than leak it in chunks. I'll let you know kind of all of it once I know all of it, but I'm totally down to pass on the info that I have. Canvas, the Canvas multiple choice for exam 3. Ooh, that looks sloppy. All right. So here's what I've got so far. Not so far. I've finished writing it. So there will be 30 questions. 30 questions and an unknown amount of time to complete it. I haven't nailed that down yet. So that's to be determined. And then the concepts that'll be on the multiple choice. So you'll have quantum numbers, because those didn't make it onto exam 2. We'll have electron configurations. There will be questions about VSEPR. Oops. And actually, I want to bump the VSEPR down a little bit. We'll have there's periodic trends. Electronegativity, atomic radius, ionization energy, electron affinity, that stuff. It'll be less. I am still planning on time to be tight, but I don't want the crunch to be as big as last time. And again, I haven't thought that through completely. So we've got VSEPR, periodic trends, and intermolecular forces. All right, and so the and we have sorry. Want to bump VSEPR down one more. Oops. There are some hybridization questions on here as well. All right. So the percentages for each. So for quantum numbers, about 20% of the exam, or of the questions, are on quantum numbers. 20% are electron configurations, periodic trends, will be 6.7%. Intermolecular forces. Oh yeah. Here we are. Yeah. Let's see, where are the intermolecular forces again? There we go. 13.3%. Hybridization. 13.3% of the questions are on hybridization. And then the VSEPR comes out to be 26 point, actually, let's be a little more, 26.7% will be VSEPR questions. Totally. So this is kind of the breakdown. When and I guess I can clarify a little bit here. When I say VSEPR, some problems ask for geometry. Some problems ask for bond angle. So that's kind of that breakdown there. So this is what you can expect. It's going to be 30 questions. Again, an unknown amount of minutes. The questions are definitely easier. Just by the nature of them, you can see that there aren't really any calculations involved. Probably the hardest part will be the intermolecular forces, because that's the newest topic. So I would definitely review that on your own this weekend. You definitely have enough to assign London dispersion, right? Anything with electrons. And dipole-dipole. We'll talk about what hydrogen bonding is, but that's even something, if you wanted to, you could read ahead on your own. Yeah. The VSEPR stuff, definitely memorize. Because it'll save you time. Right? Theoretically, you could just look it up, but that's time that you have to spend, like, finding it out on a chart, looking it up, all that stuff, as opposed to if you just have it memorized, you'll be hitting that VSEPR stuff, which, as you can see, is a quarter of the test, and just, you'll, like, look at it, you'll know it, you'll put down the answer, you'll go to the next problem. It'll give you more time for the other problems. Excuse me. Sorry for that yawn. As my grandfather used to say, it's the mileage, not the company. I'm yawning because I'm tired, not because you're boring. is a paraphrase of that situation. So this is what I know about the Canvas multiple choice exam. As I said earlier, I will be making a more comprehensive post to Canvas about the test when I know more, including announcing how long you'll have to take it, etc. Those determinations have yet to be made, and I need to write the take-home. So, I've got some work cut out for me, but that post should be dropping probably sometime this weekend. So keep an eye open for that. And with that, are there any other questions out there? Because I'm totally down to answer them. Let's see, what about the take-home? Great. What about? As of right now, I only know that you will have a take home. I haven't sat down to start writing it yet. My focus has been building the problem bank for the multiple choice exam, which is now complete. So so after actually I conclude this stream, I'm going to sit down and start doing some brainstorming, planning, writing problems for the. Oh, okay, sorry. Now I gotcha. Now I gotcha. So it'll have um right. So the material on exam 3 is everything after the exam 2 cutoff. So exam 2 did not include the quantum numbers from chapter 7. So that is the first eligible. That is the first eligible topic that can appear on exam 3. So everything after that can appear. Everything after that will be represented between the multiple choice and the take home, but not necessarily everything on the multiple choice will be on the take home and vice versa. So, because it's kind of, I actually, for example, usually on my exam 3 put quantum numbers problems as multiple choice. So, so the fact that they're going to be on the multiple choice part, they may or may not show up on the written. I haven't decided that yet. Okay, yes, totally. Yeah, the final will be everything. Yep. Totally. So the final tests on everything in the class. It is what you call cumulative. So that's as much as I know about the third exam and the final exam. Let's see. Canvas multiple choice opens up and closes when? Great question. Let me check really quick, actually. I know this because I've already said it. I haven't published it yet, though, because I'm still finishing the final formatting details. So, hang on one second. I'm logging into Canvas. Doot, doot, doot. And go to the secret quizzes. Let's see. Okay, there we go. Hang on. Okay. Yeah, so here, that is a great question. Ba-dum-ba-dum. So Jesse, here's the answer to your question. So the multiple choice, um, the multiple choice exam opens on, where is that? It opens up at 3 p.m. A week from today on 5/13. It closes at 11:59 p.m. The following day. So that Thursday. So the window that you'll have to take it is larger than a 24-hour window, but the amount of time that you'll have to take it is the same no matter when you... Well, you'll have the same amount of time to take it no matter when you start it, assuming that you start it before like 11:58. Because if you started at 11:58 p.m. on 5/14, then you'll have 1 minute to take it. So as long as you give yourself enough time to take the full exam before it closes, then you have the same amount of time as everyone else. But you can start taking it at any moment in that window. So that is when it opens and closes. Again, it will be getting published soon. I'm just doing the last... I've written all the problems. I'm just in the last stages of formatting this thing. Of course. Anytime. Cool. Well, I think, unless there are any last minute questions, I'm gonna put a pin in this stream. Thanks everyone for coming out, for the humans who hung out with me live, and any humans watching after the fact. Don't forget you can hit me up for office hours on Friday at 1 p.m. If you have any lingering questions, or maybe if you give that problem that I wrote up on the board at the beginning of lecture today, give that a try. Maybe you'll get stuck. Maybe you need some help. Hit me up. We can talk about it in office hours. Yep, there's totally office hours on Friday. Absolutely. So we'll have a chance to get into more stuff. Then here's me signing off for the second to last Wednesday we have together, our penultimate Wednesday. I'm going to try to sneak that word in as many times as I can here at the end of the semester. All right, dudes, it's been an awesome stream. I will catch you all, some of you Friday, the rest of you I'll see on Monday, where we wrap up Intermolecular Forces. Later.